We are now into a set of videos on Earth's magnetic field. There are 5 videos. The first 2 describe the geometry and the time variation of Earth's field. Then in the 3rd video, I'll talk about what generates Earth's magnetic field. The last 2 videos look at how rocks record Earth's magnetic field in the past and how we use that information to analyze plate tectonics. Are you ready to begin? Okay, let's lift to the learning goals for this video. First of all, I have to remind you of some basic definitions and terms in magnetics. Then I will go through describing Earth's magnetic field, its geometry, and the geometry includes a description of a vector with inclination, a dip angle, and declination, a direction to the magnetic pole. We'll need to talk about the strength of Earth's magnetic field and learn what the difference is between a dipole magnetic field and non-dipole magnetic fields. Okay, let's go on to some basic magnetics. We use 2 symbols for magnetics. There's B, which is described as magnetic field, and H, which is called the magnetizing field. Now, unfortunately, in various textbooks and sources, you'll see either B or H called magnetic field. You have to look carefully to see which is which. The difference between B and H is subtle. In outside of magnetic materials, B and H are related by a constant, the magnetic susceptibility of free space. So B is equal to mu naught times H. Now, the difference really comes in inside of magnetic materials, where the magnetic field B is equal to the magnetizing field H times the susceptibility plus a magnetic polarization of the material. So the second term, J, is the magnetization of the rock adding to the magnetic field. So, remind you again, B and H have both been called magnetic field. You have to look carefully to see which is which. Now, the total magnetic field is a vector quantity B, and it has on Earth's surface a vertical component Z and a horizontal component H. Now, unfortunately, H could be confused with the magnetizing field H, but you have to look carefully to see when we're talking about a horizontal component of Earth's magnetic field and when we're talking about H, a magnetizing field. So if you have a vertical and horizontal component of magnetic field, simple trigonometry that the angle between horizontal and the direction of the magnetic field is given as the inverse tangent of the ratio of the vertical to horizontal component. Now, declination is the direction angle between H and true north. So the horizontal magnetic component is not pointed directly at the North Pole. Thus, there is an angle we call the declination. Finally, the tangent of the inclination is equal to twice the tangent of the latitude. Now, this is true if the Earth has a perfect dipole magnetic field that is centered at the center of the Earth and aligned with the axis of Earth's rotation. It's a little more basic magnetics. The units of magnetic field. Well, there's the Tesla, which is a SI unit, and there's the gamma, which is a CGS unit. Conveniently, 1 nanotesla, which is 10 to the minus 9 teslas, is numerically the same as 1 gamma in CGS units. Now, to give you an idea of relative strength of magnetic fields, a 3 Tesla magnetic field is extremely strong, and it's the kind of magnetic field that is used in top-end medical magnetic resonance imaging machines. However, the kind of magnetic field associated with a refrigerator magnet is much less. It's a half of a millitesla, and a millitesla would be thousandth of a Tesla. So 5 times 10 to the minus 4 Tesla is a refrigerator magnet strength. Finally, we have Earth's magnetic field, which is about 70,000 nanoteslas, and you multiply 10 to the 9th times 70,000, and that gives you 7 times 10 to the minus 5 teslas. So strength of magnetic field at the magnetic pole where it is strongest is about 7 times 10 to the minus 5 Tesla. Okay, there are some instruments used to measure magnetic field, and I'll just give you their names. You can go to Wikipedia or other references to see how they actually work. Flux gate magnetometer is a long-standing core instrument in geophysics of Earth's magnetic field. The flux gate magnetometer measures a vector component of the magnetic field. Therefore, you need 3 flux gates to measure 3 components to get a full vector representation of Earth's magnetic field. A flux gate magnetometer is capable of measuring magnetic field to about 1/10 of a nanotesla. Another instrument used to measure magnetic field is a proton precession magnetometer. Unlike the flux gate, it doesn't measure vector components of the field. It simply measures the total strength of the field, and it measures it to about 1/10 of a nanotesla. Finally, the modern instrument for measuring magnetic field is a SQUID, which is a superconducting quantum interference device. SQUIDs measure 3 components of magnetic field to extraordinarily high precision. They're measured in attotesla. And then what is an attotesla? It's 10 to the minus 18 of a Tesla. Let's turn to a description of Earth's magnetic field now. We can look at map coordinates looking down at the Earth's surface with north upwards and east to the right. Now, a compass needle laid down on a map is going to point in some direction other than true north in most locations on Earth's surface. That angle between true north and the direction the compass needle points is the declination. In this example, the declination is about 40 degrees to the east of north. You would write that as north 40 east. Now, Earth's magnetic field is a vector quantity, so we need to go into 3-dimensional space. So let's turn our map on its side where we have the horizontal surface being Earth's surface, and then we have down illustrated in the down direction. We can now put a magnetic field vector, there it is, dipping into the Earth's surface and pointing some direction not quite to pure true north. Now that vector can be deconvolved into 2 components, a horizontal component and a vertical component. So the sum of the horizontal and the vertical component gives you the full magnetic field. Again, I'll show you there's the angle from true north to our horizontal component that we describe as the declination, and then there's the angle from the horizontal direction down to our dip direction, and we call that the inclination. Now, let's take away everything and just look at our 3 vectors. We have the horizontal component, a vertical component, and an angle between the horizontal and vertical component. The total field is a vector addition of h plus z, and there's the angle I between h and b. Now that angle I is, by trigonometry, the tangent of that angle is equal to z over h. Well, let's step it back now and look at the entire Earth and its magnetic field. And starting point is to look at a dipole magnetic field. So here is a dipole magnetic field superimposed on a cross-section through the Earth. I've put the dipole at the Earth's center, and I've aligned it more or less with the rotational axis of Earth. Features that you see in this, well, there are 2 poles, the north pole and the south pole of the magnet, and you can also see that there is a variation of separation of these lines and in the direction in which they are oriented relative to Earth's surface. The lines are closer together at the poles than they are at the equator, and that leads to very much stronger magnetic fields at the pole than at the equator. In fact, the equator is about half the strength of the magnetic field at the poles. I can superimpose a coordinate system on our drawing with an axis coming out the equator and out the North Pole. The angle measured from the equator then upwards is lambda, the latitude. Notice then that the magnetic field lines are striking the Earth's surface vertically at the pole. They're coming straight in and towards the dipole at the Earth's center. At the South Pole, magnetic field lines are leaving the dipole into the magnet and coming out through the Earth's surface. There is then a connection of those lines going around, circling around and back in. So at the magnetic equator, the lines of magnetic force are parallel to the Earth's surface. Now notice as you move from the equator northward, the magnetic field lines begin to dip into the Earth's surface. They are dipping at a shallow angle near the equator, and that angle gets steeper and steeper as you get closer to the pole. Likewise, in the southern hemisphere, the lines of force emerge out of the Earth's surface. They dip upwards, and the angle gets shallower as you go from the South Pole towards the equator. The relationship of the dip angle I and latitude is simply tangent of the inclination equal twice the tangent of the latitude. Okay, now let's look at a magnetic field that is not dipole-like. And how do we make a non-dipole magnetic field? Well, the easiest way, and the first one to look at, is the quadrupole. So a dipole has two poles, a north pole and a south pole. A quadrupole, quadra, four, means there have to be four poles. So let's look at it. Take away the fields, and here's just a single dipole magnet with a south end and a north end. I can move that and place a second dipole flipped around in the opposite direction. So you see we have two norths put together and south at either side, top and the bottom. Now magnetic field lines will leave this quadrupole at the north and circle around and come in at the south end. So there are field lines emerging from our quadrupole, the north end of the quadrupole, and there are field lines coming in at the south end. There has to be a complete connection of these magnetic field lines. So the overall pattern of magnetic field for a quadrupole is as shown here in the yellow. You see lines emerging at the equator and converging and descending into the Earth at the poles. You notice that there are loops of magnetic field in four quadrants here. So it's like the quadrupole, there are four quadrants. Okay, so at the Earth's surface, the direction of the magnetic field is vertical and inward at the poles. It's vertical and outwards at the equator. Remember, for a dipole at the equator, the magnetic field lines were horizontal. Here they are vertical. In mid-latitudes, both in the north and the south, you see there is a point at which the magnetic field lines become tangent to the Earth's surface where the inclination is zero. So in the case of the dipole, we only had zero inclination at the equator. For the quadrupole, now we have a point in both the northern and southern hemisphere where the field lines become tangent to the Earth's surface with zero inclination. So now we're in a position to talk about the overall Earth magnetic field. In general, the largest part of Earth's magnetic field is dipole-like, but there's about 20% of it that is non-dipole-like. And the largest non-dipole contribution to Earth's magnetic field comes from quadrupole fields. But there are additional higher order magnetic fields from multipoles that contribute to the total field. So a quadrupole has two dipoles together. An octopole would have two quadrupoles put together, and so forth. we can fit a dipole to the Earth's magnetic field, and the best fitting dipole positioned at Earth's center is inclined by about 11 degrees from Earth's rotational axis. So here's the picture. You can see we've represented Earth's magnetic field as originating at the center of the Earth from a dipole. That dipole is tilted. So we have a geographic North Pole as indicated there coming in the top, and we have a magnetic North Pole that's off in the direction towards the Baffin Islands in northern and northeastern Canada. The strength of the magnetic field near the poles is about 70,000 nanoteslas. At the equator, it drops as low as 25,000 nanoteslas. You have magnetic field lines coming out of the Earth in the southern hemisphere and coming into the Earth in the northern hemisphere. So that's Earth's magnetic field in the big picture. Here's a map showing lines of constant latitude across it. And if the Earth's magnetic field were dipole-like and oriented with the spin axis of the Earth, then both intensity and inclination would vary only with latitude, and thus these lines would be lines of constant intensity or constant angle of inclination. If I tip the Earth's magnetic field and I step over here, now you can see this is for a tip of 11 degrees, and you can see how the field varies with latitude, and you see some wiggles across the Earth's surface. So they're fairly subtle features, a little wiggle. You see across Asia it goes up, and across the Americas it goes down and comes back up around Africa. Now, if I compare that with the actual measured magnetic field of the Earth, which I've brought in here, this is a plot of the angle of inclination of Earth's magnetic field, and you can see that compared to the purely dipole field, there's some fairly major swings that don't show up in the pure dipole. You can see between South America and Africa, it swings up, and across Asia, there's an extra wiggle that doesn't show up in the purely dipole representation. If I bring up the intensity maps, here's contours of constant intensities. You see the overall dipole appearance. The magnetic field is strongest near the poles, over 60,000 nanotesla, and the 60,000 nanotesla contour shows at both the north end and at the south end. And magnetic field strength drops as you go from the poles towards the equator, with equator having magnetic field strengths of less than 30,000 nanotesla. And you see around South America there's a low point where the magnetic field strength's dropping below 25,000 nanotesla. So this is definitely overall 80% dipole-like, but then superimposed on that is some additional behavior that is non-dipole-like. So that brings to an end my discussion of the geometry of Earth's magnetic field. Coming up, I want to talk about how Earth's magnetic field varies in time.